So the question says, balance the following reactions. What type of reactions are these? So here we have C3H8, which is propane, reacting with oxygen to form carbon dioxide and water. So these reactions are combustion reactions. And in a combustion reaction, the hydrocarbon, in this case, reacts with oxygen to form carbon dioxide and water. So you may have heard that, burning fossil fuels releases carbon dioxide into the atmosphere. This is why, because these hydrocarbons, react with oxygen, and the stable products are carbon dioxide and water. These stable products also means that this gives off heat. So this is the stuff used in a barbecue grill. This is very similar to a molecule used in gasoline, although this one is benzene, and gasoline has a fair amount of toluene in it, although gasoline is a complex mixture, but it is molecules related to this one. So this is basically how this works. So in this case, you want to, for combustion reactions, balance in the order of carbon, then hydrogen, then oxygen. And when you're burning simple hydrocarbons, which are molecules that only contain carbon and hydrogen, they're going to be written in the order carbon, then hydrogen, then oxygen, so it's easy to remember them. It actually doesn't matter if you balance carbon first or hydrogen first. What matters is you balance oxygen last. And the reason for that is it's in both products, so it's easiest to balance it last. So let's take a look here. We have C3H8 plus O2. So carbon, all of the carbon of the hydrocarbon goes into carbon dioxide. So if we have C3 here, we're going to need 3 carbon dioxides. At least that's our first best guess. Sometimes you have to double it, as you'll see. Here we have 8 hydrogens. Each water contains 2 hydrogens. So all of the hydrogen of the hydrocarbon goes into water. All the carbon goes into carbon dioxide. All the hydrogen goes into water. But in this case we have H8. In this case we have H2. So we're going to put 4 for the H2. All right, so that'll give us our 8 H's because we have H2O. So now let's look. We have 3 carbon dioxides. Each carbon dioxide contains 2 oxygens. It's a carbon bonded to 2 oxygens, which means we have a total of 6 oxygens here. In this case, we have 4 waters. Each water is an oxygen bonded to 2 hydrogens, so each contains 1. So we have 4 more O's. 6 plus 4 equals a total of 10 oxygens on our product side. Remember that this is O2. So how many O2s do we need? We would need 5 O2s. So this will be a balanced chemical equation. Let's check. We have 3 carbons, 3 CO2s is 3 carbons. 8 hydrogens, 4 H2Os is 4 times 2, which is 8 hydrogens. 10 oxygens, 3 times 2 is 6, plus 4 times 1 is 4 more, for a total of 10 oxygens. We're good. It's a balanced equation. Let's look at benzene down here, which again is related to molecules you would find in gasoline in this combustion reaction. So here we have C6H6. It's the same thing. All of the carbon ends up in carbon dioxide. So our first best guess is we're going to need 6 carbon dioxides. Now let's look at 6 hydrogens. Well, all of our hydrogen goes into water, so we need 3 waters because each one contains 2. Now let's add up our oxygens. We have 6 times 2, which is 12 O's, plus 3 times 1, which is 3 more O's, for a total of 15 oxygens. This is a problem. What's the problem? The problem is that 15 O2s would mean 7.5. You're not allowed to put a fraction here. It has to be an integer, right? You can't put 7.5 or 7.5. So we have to make it an integer. The easiest way to deal with this is to double everything. If we make 2 of these, we'll need 12 of these and 6 of those. Now we won't need 15 over 2 oxygens. We'll need the whole 15 O2s. So if you get an odd number of oxygens, you simply just double everything. Let's check. We have 2 times 6, which is 12 carbons. 12 CO2s is 12 carbons. 2 times 6, which is 12 oxygens. 6 waters, because each water contains 2 hydrogens, or 6 times 2 is 12 hydrogens. Carbons, we have 30, oxygens, we have 30. 15 times 2. Here we have 12 times 2, which is 24, plus 6 more, which is 30.